a sequence that shows up in grids, in trees, in mountains, and even in parentheses. Behind every mathematical pattern lies quite a beauty. Welcome to one of the math's most elegant families, the Catalan numbers. Imagine a grid. You want to walk from one corner to the opposite corner, but you can only move up or right. Simple, right? Now, here is the twist. What if you are not allowed to cross the diagonal line? How many such paths can you make? That simple question opens the door to one of the most fascinating sequences in mathematics. Let's start with basic. On a 4 by 4 grid, every path to the top corner is just a sequence of moves, 4 right and 4 ups. The total number of ways to arrange those is simply 8 choose 4. That is 70. So 70 possible paths in total. Now the constraint is that if all the paths are below the diagonal line, remember you can't cross the diagonal. So only some of those 70 are valid. A valid path is strictly below the diagonal and invalid path that crosses it. So how many valid paths is there? So for this we have a clever trick, that is the reflection principle. Take the invalid path that crosses the diagonal, reflect that part of the crossing point, that new reflected path ends up higher at the point 4, 5. So the counting the invalid paths is same as counting the paths to that higher point. It's symmetry. Hidden, plain, side. So total paths is 70, invalid reflected paths is 56 and valid ones is 70 minus 56, that is 14. And that's the fourth Catalan number. We have just discovered Catalan sequence in disguise. In general, the number of paths that stays below the diagonal is given by a beautiful formula. And with the help of that formula, we can get C0 is 1, C1 is 1, C2 is 2, C3 is 5, and C4 is 14. Catalan numbers quietly count the structure after structure. Catalan numbers aren't just a combinatorial coincidence, they grow recursively. Each new number is built up from the sum of all the possible pairings earlier ones. Now building C4, that is equal to 14. Each term is a sum of the products, as C0 is 1 and C3 is 5, so the product is 5. So the sum far is 5. Similarly, C1 is 1 and C2 is 2, so that gives us equal to 2, and the sum so far is 7. Similarly, C2 is 2 and C1 is 1, so the product is again equal to 2 and the sum so far is 9. Moving on, C3 is 5 and C0 is 1, so that gives us equal to 5, which makes the sum equal to 14, and which is the building for C4. In a similar way, we can just look at the general pattern. The general pattern will be Cn plus 1 is equal to the summation from I is equal to 0 to n Ci into Cn minus I. We can get with the help of age. For each ways to split n elements, I elements on the left, n minus 1 elements on the right, multiply their Catalan numbers. It's just like a tree branching into smaller trees. It's mathematics building itself from roots. Catalan numbers appears in geometry too. Take a pentagon. How many ways we can draw non-crossing diagonals to divide it into triangles? The answer is 5 and exactly the same as C3. Different problems, same number. The Catalan sequence quite connects them all. The general formula for the Catalan number is Cn equals 1 divided by n plus 1 times 2n choose n. The first few Catalan numbers are C0 that is equal to 1, C1 is 1, C2 is 2, C3 is 5 and C4 14 and C5 is 42 and so on. Catalan number counts so many things, the number of ways to correct parenthesis expressions, the number of branching trees with n plus 1 leaves, the number of mountain ranges that never dip below the sea level. Different words, same number, isn't that beautiful? One simple constraint, countless structures, that's the elegance of Catalan number. A quiet reminder that even the simplest rule can lead to infinite wonders. Thank you for watching, and as always, stay curious.
You enjoyed this visual proof? Make sure to like, share, and subscribe for more math explained visually.